Hey, math people, we're finally starting our journey through graphing in 3 space. We got to start small, though, with lines. All right, so you had your mx plus b day back in Algebra 1. Now you're going to have it in Calc 3. Looking at the overview, we're looking at some intuition building. We'll define the equation of a line. We'll do some examples. We'll define one last form, another example, some kind of funner extensions, and then talking about like systems of lines in space. Okay, so remember this video is for you, Bailey. So what does that mean? It means you can click around and pause the video and use the timestamps as you need. This can be a practical video. You just got to use it as such. All right, so here we go. Right off the bat, we're looking at just a little warm-up lead into what's to come. Lines in R2 were once determined by a what and a what. What were the two things you needed to sketch an equation of a line? In R2, you needed a point and a slope. In R3, it's close but not quite the same. It's a point and a direction vector, because here's the thing. No longer is, so in this case, 3, and y is equal to, no longer is 3 over 1, like adequate to describe the change in space, right? Consider how 3, or 3 over 1, communicates change as we kind of increase our x values. We're not just increasing x values to determine some change in z, but we are instead increasing some y values as well. So, all right, we have change in 2 different directions. What does that call for? It calls for the use of a vector right away. You know, that's the whole point of covering vectors in the way that we did. Anyway, let's try out this new idea on the plane first. So given the point 2, 3 and the point 6, 8, nothing too crazy. I mean, I'll even sketch them. On the plane, I want to now utilize vectors with something we already know and love, right? We can come up with point slope for this line. I know you can do that. I think you can do that. I hope you can do that. But how can we utilize a vectored approach to come up with such an idea? Okay, well, the idea is not that bad. It's to find the vector a, b, by subtraction. So if you were to find the vector that connects 2, 3 to 6, 8 here, you would get the vector 4, 5. And you can see it like this. Well, all right. When I create a vector that connects a to b, there's a lot of points that exist on that vector. In fact, there's an infinite number of points. We'll just call it arbitrarily some point p, x, y. If I then want to define the vector, the vector pa, so that would be connecting from P to A. It's on the same line, right? Well, what I would do is I would do the same subtraction idea I did above. I have x minus 2 and x minus 3. Here's the thing. These two vectors are scalar, this vector and this vector, they're scalar multiples of one another, right? Because they're pointing in the same direction. So the vector connecting P to A is not the same vector connecting A to B, but they're pointing in the same direction. There is some number I can multiply 4, 5 by, so some number, to get this vector PA. And that's the whole premise, is that these are the same. So what we can do thereafter, just doing a little multiplication with the scalar, this is 4k and 5k, sure. I would know that x minus 2 is equal to this 4k, and y minus 3 is equal to this 5k. Set them equal to one another, and you end up getting you can say k is like t, like a time component. You end up getting x is equal to 4t plus 2, and y is equal to 5t plus 2. I will connect that to parametric equations. Remember, I needed parametric equations back in, actually I want to keep these, back in probably Calc 2. Well, look at this. 4t plus 2, generally t is what's used. K would have been just fine, but 5t plus 3, you can think of it as like a time. Oh, here we go. You can think about it as like a time component. So like as I kind of move along, actually, if I use k, I think k would actually be better. Check this out. Check it. If I make it a k, it's kind of like your location in time. Oh, there it is. Yeah, there it is, right? It's your location in time. So, say 0.9 seconds in, traveling from 2, 3 to 6, 8. This would be my location. This whole trick of it occurring from 0 to 1 was sort of by design in a lot of ways. But the whole premise is that this is just one way. So what we did was we parameterized the line in terms of its x component and y component. We now want to sketch in space, so we just need to parameterize a line with respect to its x, y, and now z component. That's it. Here, z would just be equal to 0, but if we just add another component to a and b, it would just be the same process, but with some z equation. Nothing too crazy. What I did above was this. I have like a y is equal to mx plus b idea in mind, but with vectors instead. So I have some sort of initial point, and then plus like my slope, my direction vector is what this a, b, c would represent in relation to slope, right? It was once slope, it's now a direction vector. And you can do vector multiplication and addition to establish this this equation. If we were to set the respective components equal to one another, x would be equal to just your starting x value plus your slope in the x direction times your time component, you can say, and then the same corresponding idea for y and z. So this is the same idea as we saw above. So consider how this vector right here is the same thing as vector of components x, y, and minus vector of components 2, 3. I can like add that 2, 3 onto the right side. Hey, that's the initial condition, the initial point right here, x naught, y naught, z naught. The b in your y is equal to mx plus b. And then you have your like slope or your direction vector, which was 4k plus or comma 5k in this case. And then over here, it's just your t times your direction vector a, b, c if you add a z component. They're the same thing. Let's see this in practice right away. New idea in space. Given two ordered triplets, we want to come up with the equation of the line that connects a to b. Went ahead and graphed them. Here they are. So what's the equation of the line that connects the two? Well, see if you want to practice this on your own. Come up with the direction vector, which is the difference between these points, right? So difference in x, difference in y, difference in z. And then use one of them as an initial point. How about we use a for sake of convention here? So a lot more doable than you think. Give it a go. 3, 2, 1. Not that crazy. Not that crazy. The vector AB is our direction vector. So the way we find that is 6 minus 2, that's your 4. -8 minus -3, that's a -5. Same idea for the z component, you get -6. This represents my direction. Well, if I then use A as my initial point, I can then come up with each of these components. That's pretty sweet. So how about I graph this parametrically? I start at an x value of 2, and then my direction vector's x component is 4. I start at a y component of -3, and then my direction vector y component is -5. And then lastly, I start at 5, and my direction vector's z component is -6. So I'm going to do 5 minus 6t. Here we go. Right, so that would be your parametrically defined equation for the line connecting the two. Sweet. Anything else I want to say to this? Okay, so yeah. This would be the set of parametric equations that create this line, right? That is different from like a point traveling from. This is not a vector. It's not a point. It's the parametric equations for the space curve that is a line. Just a little nuanced with this language. These are parametric equations. You can package them together instead of having it as 3 separate equations inside of a vector equation. But that's just a packaging methodology. This in itself, this blue connection is not a vector, and it is not a surface. It is a space curve defined by parametric equations. Just some ramble. Sorry, I got to do math teacher ramble. Sorry. All right, but wait, there's more. Is it possible to express this line as a string of equations rather than a package of 3 or a vector equation? Yeah, you can. Here's how you do it. So what I noticed is that each of these equations have one variable in common, and that variable is t, this like time variable. And I say time because it doesn't have to necessarily be time. What I can do is I can solve for t in all 3 of these equations, okay? And then, well, I know that t is equal to t, right? So I can just set all 3 of these expressions equal to one another. Yeah, so this is the symmetric equation, because there's technically like 3 equations here, of a line. This is secretly slope, by the way, all along, right? So like just looking at the x and y components, what you could do is you can cross multiply here. And after you do that, divide out the a, divide out the changes in x, and you get that change in y over change of x idea. You can do the same thing to determine the slope on the xy change, xz change, and yz change. So it's just secretly including all of those slopes together in one package. All right, let's do another one, and let's practice writing it in all 3 ways. Direction vector is not that bad. It's just a difference. Use A as like our initial point, and then practice writing it as the vector equation, parametric equations, and symmetric. 3, 2, 1. All right, coming up with that direction vector, not crazy. It's 4, 5, -8 by subtraction. And if we were then to write the vector equation, we know that this is the direction vector. So I'm just plugging and playing into the formula, really. My initial point is A. You could have used B just fine. It would have been the same thing, right? Now, it would connect. Here, I'll show that mild difference. Super small difference. Super small. Oh, the other thing about what I just graphed here, though, the answer isn't a segment. It goes on forever. It goes on -infinity to +infinity. So it was a line, not a line segment. And that's going to be important for the intuition I build here. -3, 0, 6, and then 1, 5, -2. So I'm creating this line. Of course, this would work just fine. I'm writing this as parametric equations. -3 plus 4t, and then I'll just write it this way. I'll write it as 0 plus 5t, and then 6 minus 8t. Right, this is the line segment when I confine t to be between 0 and 1, but of course this goes on forever, so I'll just do -99 to 99. This is the real line. So what if I started at b instead? What would that change? Well, here's what it would change. In respect to the whole line segment, literally nothing. Literally nothing. You can start at 1, you can start at 5, and you can start at -2. Right? And it's the same exact line. You're just starting at a different point. And then like where you are at time 2 or time 3 would change if you're plugging in a particular value. But you'll also notice this. If I were to like be concerned with the segment connecting 0 to 1, it's like a different like little snippet of the line. But remember, it's a line, not a line segment. So it's the same shape. -99 and 99, we'll say. There it is. Same shape. Doesn't matter where you start. Same thing with lines in the plane. All right, so that's parametric equation, starting point, and then all your direction vector. And what you could do is you can solve for t, solve for t, solve for t, and then just set them all equal to each other for the symmetric equations. All right, so looking at the same line up here, where does L intersect the xz plane, xy plane, and then yz plane? Let's think about this. On the xz plane, what is y equal to? Same question for 2 and 3. What is z equal to and what is x equal to? How can you utilize that with these equations? That's my hint. 3, 2, 1. All right, well, you're just plugging in 0 for y. So this was given for the first one, right? It just straight up gives you that a, and we can look at a. Point A is purple. You can see that purple is on the xz plane. That's when y is equal to 0. Extend that up, and you can see it intersects at that moment, right? All right, so they gave you that one. That was kind of like a trick question in some ways. You didn't have to do any work for it. For the next one, though, when z is equal to 0, I'm just setting z is equal to 0 within one of my components, or one of my components, my z component. And then I can solve for t. That will give me like the time where we have a z value of 0, which is on the xy plane. That's at 3/4. I went ahead and I plugged that into the x parametric equation and the y parametric equation, and then I got the exact ordered pair where this happens. So I guess it happens at 0, 15/4, 0. That would be, so the xy plane is when z is equal to 0. So that happens right here. And I'll make it a different color. It is orange. Now this is a little confusing though, because this point is also on another plane, right? So use your work from above. Like, yeah, I can plug in x is equal to 0 and I can find that time value, right? Sure, and I can plug that into the z component and y component, but it's the same thing. You're gonna get 3/4 as well, right? And that should actually make sense from the values, right? If you were to set 0 here, that's the same answer if you were to set 0 here. What is that? That's -6 over -8. That's the same thing as -3 over -4, just reduced down. Because orange intersects both the xy plane, but then also the yz plane. Right? It intersects right at that. Like right when the wall meets the ground, I guess. I don't know. These were a little extra, right? It was because it was a y-intercept. You have a y component, but you have no x or no z component. But it's just a good way to start or continue to build your understanding of space, right? Because we're going to be graphing with a new variable in mind, and that's not an easy process. All right, last case. What if we had a system of equations, system of linear equations, what we're used to back in Math 1 or Algebra 1, is you're used to graphing on the plane. And what you would do is you would determine the number of solutions to a system based on whether or not they intersected, right? So you're viewing me right now on the plane. So these are going to be my lines, by the way. And you're viewing me on a plane because I am on your screen, and that is two-dimensional. So this depth is hard to see. You only get that through like lighting and stuff like that, and interpretation, and your brain does brain things. So anyway, you're used to this. You're used to two lines either intersecting once, never if they're parallel, or forever if they're the same line. It's kind of the same thing with space. Same solutions, either 0, 1, or never. However, the way we get 0 can be a little bit different. We're used to getting 0 based on the fact that they would have the same slope. But now, take a look at this. It's going to be a crazy idea. It looks like, so I'm going to do a little magic. It looks like these two lines are intersecting, right, on your screen. However, I've tricked you. I've tricked your mind. What I can do is I can add that third dimension, give you that depth, and see that, hey, wait a minute. Looking at the camera here. Yeah. These don't intersect. They don't intersect, right? These lines are known to be skew. They're not parallel. They're skew. They don't intersect, but they don't have the same direction vector. It can just happen in space. All right, we're going to look at each case one at a time. Let's look at line 1 and line 2 together. My suggestion, if you want to try it on your own, is to do system of equation-y things. What if you were to write these as parametric equations? What could you do off that? If you want to just see what I do, that's totally fine with me. 3, 2, 1. All right, so looking at just line 1 and line 2. The process is this. We prefer the equations in parametric form. The thing is about that is we don't care about like this like fictitious like particle moving along the line with like the time variable, quote unquote. We don't care about that. These are static lines in space. We're just trying to determine if they intersect or not. So what we do is we use a different like time variable, like placeholder parametric variable. I'm using s here because t was already used. If I were to use t, I would be looking to see if like particles along these lines were to collide or something along those lines. So what I did off this was I set the x components equal to one another. I set the y components equal to one another. And then I got s is equal to 1 and t is equal to 2. All right, so what this is this. They would intersect on like some ST plane at 1, 2. However, we have a third dimension. So what we have to do is we have to lift under the hood to see if they are skew or not. So the lifting under the hood is going back home, taking this S value of 1, plugging it into the Z component. Taking this T value of 2, plugging it into this Z component. If they're the same, you lift under the hood, they have the same Z output and they intersect. If they're different, then they're skew. And if I lift under the hood here, we can see that they are intersecting, right? These lines intersect in space, which is why I wrote that there. So yeah, it's 4 is equal to 4, turns out. All right, let's try out line 1 and line 3. So if you're going to do anything here, you're going to write this as a set of parametric equations. Use some other variable. I think I use k. Those are just the common ones to use, s, k, and t for whatever reason. And then same ideology. So just set the x component equal to the x component, y component equal to the y component, and then check under the hood, see if the z components are the same after you take those s and k components back home respectively. 3, 2, 1. If you attempt to do that, not going to play out the same way. You get the 6 plus s equal to the 4 plus 4k. 2 minus 3s is equal to the negative 2 minus 2k. If you want to write this in parametric equations, just I would set k is equal to this, k is equal to this, k is equal to this, and then just solve for x, y, and z respectively. All right, so you end up getting an s of 2 and a k of 1. All right, so, you know, kind of hovering above. So I want to create this situation. Here we go. Kind of hovering above. Okay, so they could intersect, you know, around here, right? So I take the s value of 2, I plug it back in for L1. I take the k value of 1, plug it back into L3, lift under the hood. I'm getting that z is 3 for the first one, and then for the second one I'm getting a z value of 8, right? I don't know why I didn't show the math there, but I'm getting z is equal to 8 for the next one. 8 is not equal to 3. I lift under the hood, and hey, those are skew lines. Try to fool me. Try to fool me there with that depth. But alas, I can see in 3 space. The world is wonderful. I don't know what I'm going with that. I should stop while I'm ahead. All right, next one. We got L2 and L3. So I showed an example of intersecting. I showed an example of skew. We live in 3 space, people. So lots more possibilities. Let's see. There's actually a shortcutted approach, and it has to do with the way that I've highlighted it. So you can actually skip all the math for this one. I mean, and of course I want to give an example of each. So, all right, my question is, why did I highlight what I've highlighted? That's it. And then why is it parallel, I guess? Because that's obviously the other choice. 3, 2, 1. What? 3, 2, 1. Okay. Yeah, if you look at the direction vector for the first one, yeah? It's just a scalar multiple. It's 2, negative 1, 3. It's a scalar multiple of 4, negative 2, 6. The direction vector for the L3 is 4, negative 2, 6. These have the same slopes, same direction vectors, same slopes. Kind of the same idea. Okay, so if they have the same slopes in R2, they can either be parallel or the same lines, right? And they intersect forever. So it's either a never or forever case. You just have to make sure that they have one point in common. If they have one point in common, then they continue on forever. If you look at the initial point for L2, it's like negative. No, it's yes. What's the equation for parametric? What's the default form for that? Yes, it is. Give me a sec here. Yeah, it's just the normal outputs. Okay, so the like point that we're aware of for L2 is 3, 1, negative 2. The point that we're aware of for L3 is 4, negative 2, negative 3. Those are not the same points. So dead in the water. What we have here is not this line, this right here. We have 2 parallel lines. So they have the same slope, but they don't intersect at that same kind of starting point. So they go on forever thereafter. That's all for today. Math on.